Hi guys, this is your presentation for regression, and I apologize for the tardiness of it. This is a really complicated topic. I may end up doing some supplemental work on it and giving you a little update review next week, but I haven't decided on that yet. So for now, we're going to get started with it. There is one additional homework assignment. I have put the regression homework due next Friday. So you'll have a good couple of extra days to acknowledge the fact that this went up just a little bit late. So without further ado, here we go. So let's talk about regression. So in very basic terms, regression is another statistical tool that we're going to use. And its purpose is to examine the relationship between a dependent variable and one or more independent variables. So in the past, in this course, we haven't really looked at anything that had anything to do with one or more dependent or independent variables. But in a traditional experimental and non-experimental class, you would generally follow a discussion about ANOVA with a discussion about regression. So if you need a little bit of help with this, I'll try to put some extra resources, or you can reach out to me because I know it can be very difficult. So for the purposes of this summer, I've tried to keep it really to the point, okay? So what are some questions that regression might answer? Well, some of those questions would include things like, how much does sleep affect academics performance? And can I predict a person's income based on their education level and age? And if you look at that, sleep and academic performance are singular variables, right? I've got sleep as an independent variable and then academic performance as a dependent. So that one's pretty simple. It's one and one. But the prediction one says, can I predict a person's income? That's your dependent variable based off a combination of education level and age. So that's where this kind of gets very different from all of the other things that we've discussed in this course. All right, so let's put this in perspective and talk about it from an example that is based in the real world. So think of regression as the equation that your GPS would use in your car when you want to calculate certain variables related to your destination, right? Like the map, how to get there, the instructions, the directions. So you notice if you put in a destination and you approve a route, right? It's going to give you an estimated time of arrival, or how long it's going to take you to get there. So that GPS unit has a formula in it very similar to that of regression. So what happens is you feed the unit data on a variable. In your case, you're probably just giving it your location of where you're at right now and where your destination is. But the unit itself or your phone is going to ping GPS satellites and databases out there to feed more data about variables like distance. How far are you away from your destination? Traffic. And then your speed is continuously being input as you're going through the gyroscopic function of your cell phone. So the satellites give it some data, you give it some data, but in the end, it puts out a prediction on how long it's going to take you to get somewhere. That's what regression is. It's using known information to predict a particular outcome. Now, you might think, well, you're talking about predictions. That sounds like lines. So isn't that like correlation? Yes and no. So let's review the differences between those two. All right, so let's review the differences between correlation and regression. I know those are both topics this week, so I want to make sure you're clear in the differences between the two. So correlation is when I measure the strength and the direction of a relationship. So I have one variable and I have another variable, and they're related. And that relationship is symmetrical. X affects Y, and Y affects X, and their effect is equal. Okay? If I look at X affecting Y, and then I turn around and look at Y affecting X, it should be the same, right? There's not an equation with correlation. We just get our program to calculate a coefficient, when that's the Pearson's R. And you should be very quite familiar with the fact that we cannot imply causation through correlation. We can only state that there is an association, that two variables are linked, that Y changes in proportion to X and vice versa. Regression, not only does it predict the value of one variable based on another, it computes an equation, okay? And that equation is going to take in multiple factors in order to predict Y, okay? And over here, you've got an asymmetrical relationship. X is going to predict Y. And again, you've got to be careful. Regression is not proof of causation, but it hints at a direction. It gives us more information than correlation does. In fact, there are situations in a regression analysis where you're basically looking at a correlation. All right, so let's take it back to your time in college or high school algebra and recall a linear equation. Linear equation is an expression of a linear relationship that implies a line between x and y variables. And you're probably familiar with the formula y equals mx plus b from algebra. That is a formula that's used frequently when you're trying to get the slope of a line on a coordinate plane and all that fun stuff. You're going to see this equation underneath here kind of looks similar to that. So the equation for a linear equation is y equals bx plus a. These things don't mean the same thing, because in y equals mx plus b, b is the y-intercept, and in this equation, a is the y-intercept. So let's break it down. You have a and b that are constants, right? Those are numbers that are going to be put in. And a is the y-intercept, and it's going to be the value of y when x equals 0. And then b is your mx, the m in front of the x in the other equation. B is the slope, and it indicates the change in y when x increases by 1 point. So x increases 1. How does y increase? It might increase by 1, or it might increase by 4. I don't know. It just depends. And as it does this, it's going to come up with this line. And we're going to talk about what that line is and how it's important. All right, so let's look at this linear equation in terms of something a bit more tangible. So I have my equation, y equals bx plus a. Imagine you have a local gym and it charges a membership fee of $50. And then every month it charges $20 for unlimited use of the gym. We can calculate our total cost of the gym with a linear equation where you describe the relationship between the total cost and the number of months. Okay, so if I go in and substitute 20 for B and I substitute 50 for A, I get an equation, y equals 20x plus 50. So if I pay my $50 fee and then I have my gym membership for 2 months, 20 times 2 is 40, and then 40 plus 50 is 90. The total cost of my gym membership, including the membership fee for 2 months, is $90, okay? So in regression, we have a goal of finding a line, and we call that line the regression line, and that line is going to best fit a scatter plot of data points. That line is a model, taking your independent variables and relate them to your dependent variable, okay? So we're going to calculate the fit of a line by calculating the distance between each actual y value, the data point itself, and what we call the predicted y value, or the y hat. So mathematically, distance is going to equal y minus the predicted y. So when Jamovi is actually finding that line of best fit, one thing it wants to do is to minimize the total error in your predictions. So we don't want to predict a dot out there and have that line reach to that dot when it is an error. Okay. So every point of your data set has a true value of y and a predicted value of y. And the difference between y and y hat is your error or residual. Now, in the actual formula, we're going to square each error because we don't want positive and negatives to cancel each other out. And then we're going to sum all of this up and get this error calculation, the total squared error. So the total squared error equals, remember, the sigma means sum of, we have y, a data point, minus the error, or the estimated value of y, squared. And we sum all of those up. And that gives us our total squared error. So our regression line is going to be built so that that total squared error is as small as possible. And that's where we get that line. And it's called the least squares regression line. Least because we want the smallest squared error. So let's go ahead and break down the pieces of that equation a little bit more. So this is what we call the unstandardized regression equation. So what this basically means, though, if I'm going to have more than one measure out there measuring different components, and we're going to use those different variables to predict something, I need to standardize them because, and we do that by making z-scores, or a variation of the z-score, but this is to be able to make comparisons mathematically in the equation while accounting for different scales, okay? So our y hat is our predicted value of our dependent variable, okay? So, yeah, y hat. We just went over how to calculate that over on how to talk about it on the other side. So x is the value of your independent variable, okay? B is your slope, and that's how much y changes for 1 unit increase in x. And then a is going to be my intercept or value of y when x equals 0. So how do we calculate some of those pieces? The slope is calculated with the equation slope equals the sum of product deviations over the variability in x. And underneath here, you see how you would calculate those two things. The sum of product deviations is equal to the sum of x minus the mean of x, close parentheses, times y minus the mean of y, close parentheses. Okay? So we would calculate this piece right here for all of the data points, and we would sum them up, and we would get that sum and put it up here in the formula. I'm going to erase some of these marks because they're a little annoying to me after a while. We're going to calculate that variability in x by calculating x minus the mean of x, square it, and then summing all of those up. And that's where we get our slope. Now, the a-intercept is a equals m sub y minus b times mx. So what that does is it places the line so it passes through both means. It goes through the mean of x and the mean of y. So here is a very small example of those calculations. I don't necessarily want you to have to do all of these calculations, but I want you to see how intrinsically difficult the math can get. This is a data set that only has what, 1, 2, 3, 4 pairs of x and y. That is minuscule compared to the amount of data that researchers might have in a data set. Okay, so having to go through and calculate all of this stuff would be very, very difficult if you were going past 3, 4, 5, 10. Yeah, you can use a spreadsheet, but still, I'm talking about what can you understand conceptually and do quickly in a problem. Okay, So we have all of our x's, and you can see down here they've summed. The mean sub x is 3. So they added those up, divided by 4, and they got a mean of 3. They did the same thing for y, and we have a mean of y of 6.5. Then in this column, I'm going to take x and subtract from it the mean of x. So 2 minus 3 gives me negative 1. And we do that all the way down. And we're going to do something similar for y. We're going to take our y value, subtract the mean of y, so 3 minus 6.5, and that gives you negative 3.5. Okay. Then you're going to take the x minus m sub x, and we're going to square it because we don't need these negatives in here. So 1 times 1 gives me 1. 3 times 3 gives me 9. And there you see it. Negative 3 times negative 3 also gives me 9. And we've gone ahead and summed it up down here because that just makes it easier when we go to do our calculations. All right. And we do the similar thing over here with y minus m sub y squared. Okay, so these numbers squared. And then over here, we take the product of those two numbers from over here. Not the squared, but from over here. So let's go to one that's easy. Right here, 1 times negative 0.5 gives you negative 0.5. Okay? From there, it's simply a fact of plugging in the equations. So my SP is the sum of x minus m sub x times y minus m sub y, and that equals 18. And you can see that was calculated for us right there. And then the SS of x is the sum of this column right here, 20, 18, and 20. From there, I plug it into my slope equation. I put 18 over 20, I divide, and I get a slope of 0.90. And that slope tells me for every 1 unit increase in x, y increases by 0.9 units. Almost 1, but not exactly. So how do we calculate A? We use the formula right here. A equals m sub y minus b times mx. So I'm going to take m sub y, put it down there. I'm going to take b, which was the 0.9, and my m sub x, which was 3, and I'm going to multiply that out, and I'm going to get a equals 3.8. Then all you have to do is plug it into your formula right there. So if I set x to 0, my y would be 3.8. Right, so here is an example from the book. I wanted to just show you another one, and I really wanted you to see how this can get out of hand very quickly because that data set had 4. This one has a few more. So you need to find the values of b and a in the regression equation. So b is your slope, SP over SS sub x equals, and I've already done the calculations up here. So there's our 28 right there at the bottom. SP is right here, 56. I divide that and I get 2. So our slope is 2. And I need to calculate A. So I have m sub y minus b times m sub x. So m sub y is 7. That's from up here in the table. Minus 2, that was my formula. I mean my slope calculated in this formula, 2. M sub x is 4. And when I calculate that, I get negative 1. So now I can write my equation, my linear equation. Y hat equals bx plus a. So that equals y hat equals 2. And I pull that from here. 2x minus 1. And that's what that line looks like, okay? Y hat equals 2x minus 1. And so they've drawn this nice line here that goes up that way, okay? But you notice my data points are all out here. It'd be impossible to draw a line that hit all of those data points. So this is just simply the line of best fit. So I can, this was the same that we already did there. So this was, I'm sorry, no, it's not the same. I apologize. This was just another example of a short little 3-paired data set. If I ask you to calculate something on the quiz or the test, it's going to look like this. That is why I put that in there. I might ask you to come up with that equation based on some data. So if I were you, I would highlight this like in my notes, the last 2 or 3 slides, so that you would have a quick and easy reference and know what we're talking about when we say, the slope and the y-intercept and etc. Okay. So another piece of the equation that we need to take into consideration is a factor called the standard error of the estimate. So the standard error of the estimate, the SEE, tells you how far off your predictions tend to be on average, okay? Remember that line of best fit is predicting over there, and as you saw, many data points were off of that actual line. If I extended that line out, it would pretty much be a similar thing. I'm estimating points in the distance in the future if I extended the line, but in actuality, there is some amount of error involved in that because they're not all going to be on that line, okay? So in other words, we're going to use a regression line to predict y hat. And the problem is the actual values of y aren't always on the line. So we need this standard error of the estimate to tell me how much those predictions are off by. Okay. So conceptually, it's a measure of your accuracy with your prediction. So when you have a smaller standard error of the estimate, your regression line is going to fit that data more closely. So you might have your line and your dots might be closer to it, right? Versus a situation where you have a larger SEE. So you have your line and you've got more spread out dots. They're more scattered and they're not as clustered around that central line. So you need to understand that as part of that calculation, Jamovi is going to use a formula to calculate the standard error of the estimate. So that standard error of the estimate is the square root of the sum of y minus y hat squared divided by n minus 2. So that y minus y hat, that's your difference between your actual value and your predicted value, and we call that a residual, okay? We're going to square it so we don't have any issues with positive and negatives canceling each other out. We're going to sum all those residuals that we just squared. That gives us our total total prediction error. We always have to take into consideration our degrees of freedom. So we're going to divide by n minus 2 and y2 because we lost 2 degrees of freedom, one for the slope and one for the intercept. And then when we take the square root, we're taken back to the original units of y. So you have calculated your statistic. You have this output from Jamovi. Are you going to be reporting a lot of equations? Not necessarily. There is an equation that is calculated through all of that, but what we are more preoccupied with is an F ratio that is going to be the analysis of regression. Okay, remember ratio just refers to putting two numbers one on top of the other. And the significance of that F ratio is going to be if the line actually explains a meaningful amount of variance in our dependent variable y. So how much is y varying there? Can it be attributed to this? Can that variance be attributed to something? Is it explained by our model? So your test is going to compare variance explained by your model. So how much y was predicted by x, and then a residual variance, how much error is left over. So think about it. With your GPS, you've got all kinds of factors that we talked about in there. Your location, how far you're driving, traffic, the speed that you're going to go. So a regression equation giving me that F ratio might tell me how much variance I can attribute to speed. And then it's also going to tell me how much variance is left over between all of those other variables. Okay. So if your model explains a lot more variance than what's left unexplained, you have a big F value and you have a significant result. That's what the bottom line is with regression. So let's look at R squared and your F test. So R squared is going to be the proportion of variance in Y that is explained by X, okay? So in your speed, I'm not speed, I apologize, in your time to arrive at destination, right? From your GPS. You're going from here to Dallas and you want to know how long it's going to take you. So you plug it into your GPS. The GPS is taking data and it's making a prediction, right? Well, R squared might be the proportion of variance in Y that is explained by the variable speed, or the proportion of variance in Y explained by the variable distance. That F test is going to check whether your R squared is significantly greater than 0. If it's high, it's going to be statistically significant. And what that tells you is your regression model is useful and that there is a statistically significant relationship between X and Y. That's where we get into this being similar in a way to correlations, okay? Because it's about relationships between X and Y. You may have discussed ANOVAs in the past, analysis of variance. Well, regression and ANOVA are similar to each other. And in fact, when you interpret your regression, there's going to be an ANOVA, at least one, if not two, already calculated in there. So it's important for you to understand what that means. It's usually covered more in experimental methods classes. We talk about it right here, but we don't go into the calculation of it very much. Both ANOVA and regression ask the question, how much of the variability in the outcome can we explain with a model? How much of it is just random error? And they're both going to use an F ratio to answer that question, but how they get the F ratio is a little different. So what we're doing in regression is testing our regression model using X to predict Y, and we're looking to see if it explains more variance in Y than you would expect by chance. So here's your F statistic. So you have variance explained by the model, regression, over the variance that's not explained, which is basically your residual divided by error. So your numerator is the mean squared for the model, and the denominator is the mean square error. So basically, in regression, that F statistic is calculated with this formula right here. So I hope you're seeing a pattern that I can take that formula and I can expand it to this formula up here. And then I can take that and I can go back to other things and pull out different parts. So it can get super complicated, which is why I'm very grateful that we have statistical software. But it is important for you to understand conceptually that an F statistic used in regression is how much variance is explained by my model and how much isn't. So if we have a significant correlation between Y and X, the regression equation is going to be significant. Okay, and the easiest way to break this down and to see it is to look at simple linear regression where we're dealing with one x and one y, and that's what we're going to do in just a few minutes. So Pearson's R from correlation, remember, it measures the linear association between x and y. Well, R squared is Pearson's R squared, the square of the correlation. So the F test in regression is testing if that square of the correlation is significantly greater than 0. Now, the R square is also important for something else, all right? It's also called the coefficient of determination. So on a test question, when you have an output from from a regression analysis, and you have an R squared there, and I ask you how much variance in variable Y is explained by variable X, you need to go find this coefficient of determination. So you need to look for the R squared, okay? So since there's a lot of overlap right here, I just wanted you to kind of see a little breakdown between these two concepts. So correlation is Pearson's R, and it measures that linear relationship in X and Y. A regression F test is going to say, hey, that regression model, does it significantly explain the variance in Y? So if R is significant, F will be too, and vice versa. All right, so let's look at multivariate models, and this is where things start to get a little hairy. So hang in here with me. This is why I feel like we might need another week to go over some of this part, but we're going to put it out there today, and we'll come back to it if we need to address some issues again. So let's go over multivariate models. So multiple obviously means more than one. Multiple regression is a statistical tool that we use when we want to predict one dependent variable, anxiety, using more than one independent variable. Why would we want to do this? Well, most things in life don't happen in isolation. Anxiety, for example, is likely to be a multifactorial concept. Anxiety is not just caused by fear of falling down in front of the class or whatever. There's many variables that could go into that. So you can see where this might be useful if I can contribute variance in anxiety to more than one variable. Then I can calculate how much of that anxiety can be attributed to that variable. I might be able to tackle that anxiety by targeting the factor that contributes the most. And again, that's just a very small, like short to the point breakdown of this. It's actually a lot more complicated than that, but it is what it is. So we use that multiple regression to make predictions of Y by including other predictors, because like I said, things don't happen in isolation. And at the same time, we want to control for the influence of other variables. Okay, so an example is if I want to know whether stress is a predictor of GPA while controlling for sleep and study time, I would need to use multiple regression. Okay. So in multiple regression, your formula for your linear equation looks very, very different. Actually, I shouldn't have even said linear, but whatever. We can only calculate a regression equation by hand using two predictors. After that, it has to be done on a computer. It can't be done anymore. So this is going to get a little complicated here, which is why you're definitely not going to have to calculate this part, all right? So the equation for a line in multiple regression looks like this. It looks similar to what we saw before, but as you can see here, y hat equals b1x1 and b2x2 plus a. So a is still going to be my intercept, right? But both x's, this is two predictors, right? Both x's have to be 0. You've got slopes related to each variable. So I've got a slope 1, slope 2, and those are regression coefficients. And then I have my predictor variables, my x's, and then in the end I'm looking at y hat again, predicted value of whatever our dependent variable is. So the hardest part of multiple regression by hand would be calculating those slopes or the regression coefficients. So that calculation, again, it uses the sum of products and the sums of squares. And each b value is going to be adjusted for other predictors. So unlike your simple regression formula where you had that for your slope, the math here is going to remove shared variance between x, x1, x2, x3. So what you're doing is isolating each variable's unique contribution. In other words, there would be no point in doing this. If I could not accurately separate out each x's contribution to the variance, then there would be no point in doing these tests. So down here at the bottom, you can see this formula is very complicated. So I have SP sub x1y times SSX2. It's very complicated. So thankfully we have computers. Yeah, that's how I felt. So your formula for the intercept, A, is also going to be different. Your intercept this time is going to be A equals M sub y minus B1 mx1 minus B sub 2 mx2. And if you had a third x, it would be B sub 3 mx3. And instead of placing a line of best fit, we have what we call a regression plane. So we have moved from a line into a sheet of paper, right? That plane is going to be placed through the means of all of the variables because your data is actually going to look like a cloud. So what's important to remember here? Go back to that R squared. R squared is going to be important because it's a measure of the percentage of variance that is accounted for by those predictors. So it tells me how much variance in Y can I attribute and explain using this set of predictors. So in multiple regression, we don't just look at the model being good, but we also look at which predictors contributed the most. Are some predictors redundant? And are there any predictors that are significant if I control for the others? So we can also look at exact contributions of your predictors to determine which one of them is contributing to the regression using a partial correlation, which we're not going to do that. So at the same time, when we're worrying about regression, we have this concept of covariates. And covariates are variables that are not your primary independent variable, but they're included in the regression model to control for something that might be producing a confounding effect. So we use them to adjust variables using statistics. And those variables might influence both of our variables. So covariates help us in that regression model because they adjust the model for its influence and they let me isolate that unique effect of X onto Y. Okay. Again, like I said, we live in a world where so many variables, so many things, outcome variables have multifactorial causes. And the concept of a nice, neat little equation to sum it all up is great. But in actuality, you've got so many factors. And then when you look at people in general, your personality, for example, it's been shaped by a unique set of contributing factors. So we're going to keep it to the bare bones here. So if I have an XY association and it remains significant when I control for Z, so XY are over here, and if they have a relationship, we're going to do that. And I control for Z, and it's still significant, I've got a true association. I took Z out of it, and these things were still paired with each other, so I had a true association. And it's going to do the opposite if the XY association is non-significant when I hold Z accountable there. The original association may have been what we call spurious, and it was actually caused by variable X. Okay. We have an effect that happens in this called mediation, and mediation is when the effect of an IV on a DV is actually transmitted through a third variable called a mediator. And that mediator helps us explain the mechanism that is behind the relationship. So mediators explain part, but not all of a relationship between IV and DV. And if I can control for mediation there, then I'm going to be able to isolate better effects. So IV still has a direct path on the DV, but at the same time, it's working in an indirect manner through a mediator. So mediation can be used to test causal claims, but we have to do so with caution. You've got to make sure that you have what we call temporal precedence, and we'll talk about that again in a further slide. Your independent variable has to occur in time before the mediator, okay? I can't say X caused Y if X didn't happen before Y. And the other thing I have to do is control for any other alternative explanations. So I might need to rule some stuff out by using a control variable or taking data over a long period of time in a longitudinal study. So down here you can see you've got an independent variable that's a predictor, and it is directly affecting our dependent variable. Okay, that makes sense, right? X causes Y. But at the same time, I have Z out here. And part of the predictor variable is functioning through that mediator, and you've got two inputs on that dependent variable. So what we want to do is take out that mediator so we can really see that true relationship between X and Y. Another effect that happens is there's something on my screen here. Ew. Another effect that happens is moderation. Let me get the right highlighter. Moderation happens when the effect of an IV on a DV changes depending on another variable, like a moderator. That moderator will influence the strength or the direction of that relationship. So maybe you have a moderator that's categorical, like gender, or maybe it's continuous, like sleep. So there are two graphs that I want to look at showing moderation. So let's look at the first one. So this is a graph that is showing us hours in childcare per week. Okay, hours down here. And our dependent variable is externalizing behavior problems. So an action that shows that I am upset, externalizing it, not feeling sad on the inside or mad, but going and whopping somebody else in the head. So there's a moderator variable here. It says moderator, quality of childcare, low versus high. So the interpretation of this graph is that when you have low quality care, what happens? As you go along and you have more hours, it accumulates problems. More behaviors are being externalized. More children are being hit by other children. But if you look at high quality care, as you see, it goes down, okay? So what was the moderator? Quality of childcare, low versus high. And it changes the direction of that interaction, and we call this a crossover interaction. And it's very important because, like we've said earlier today, no relationship exists in a vacuum. Here's another one using a categorical variable. So in this graph, we have the child care quality again, and we have the probability of behavior problems. So is little Johnny going to whop little Susie on the head? And this time I have a moderator, gender, boys versus girls. So what I see here is that for boys, what happens? When you go from low quality to high quality, those behaviors decrease. So boys are behaving better when the quality of the childcare increases. But in girls, it doesn't appear that quality has much to do with it. So gender is moderating the effect there. It's stronger for boys and minimal for girls. So let's go ahead and talk about longitudinal designs. Longitudinal designs are very, very important. One of the big concepts we've been talking about in this class is how to delineate between something that is an experiment or something that is not an experiment. And time comes into play with this to help you understand a little bit better about where we're going with the best design out there. So longitudinal refers to time, and a longitudinal design is going to measure some variables in the same individuals over a long period of time, usually months or years. I've never really seen anything in I've worked on a couple of studies that went out as long as 6 years. So you've got a whole other set of things and issues to worry about, like attrition and things like that. But for now, let's just talk about the designs. So longitudinal designs are great because you can track things over time. You can look at change, how much a child grew, development, how many milestones they met, or just how things change. How did their externalization of behaviors change over the course of 4 years of therapy? So those variables and the designs help us make we take observations and we can predict things over time based on that. So think about how we got the growth and development charts for children and milestones, right? We had to have tons of observations of data on things like when we expect a baby to roll over or sit up or walk or stand unaided. So over a long period of time, we've put together lots of those observations, and we now have developmental milestones that we know a child should meet by certain periods of time. So longitudinal studies are very important because they help us establish temporal precedence. Okay, and that's when your independent variable 100% happened before your dependent variable, and that is one of the requirements that we need for a causal claim. So a longitudinal study is going to help me clarify which variable came first, and so it makes it easier to argue that X really did cause Y. Why do you know that? Well, one of the reasons is that X happened before Y, so I have temporal precedence. So even a simple longitudinal regression model is stronger than a cross-sectional analysis because in part it helps support causality. Now, it doesn't support causality 100%, but it does provide another element there that helps us assure that there's a relationship that is happening there, and it is because one variable came before the other variable in terms of time. So there are a lot of different complex designs that we can get. We have cross-lagged panel models, we have growth curve modeling, we have time varying covariates, and the one that we were looking at in the previous slides, mediation and moderation. So let's talk about a cross-sectional correlation. A cross-sectional correlation is an association between different variables that are measured at the same time. So what I might do is measure two factors here, peer difficulties and pro-social behavior. I'm going to look at age 7 and I'm going to see how these two things relate. Maybe the child has increased peer difficulties and lower pro-social behaviors. So once we establish that relationship, because it's correlation, right? We can look at different points in time, different ages, age 7, age 8, age 9. But the key is every point that I'm looking at, every age. At age 7, I'm looking at peer difficulties on pro-social time together. At age 8, I'm doing the same thing. At age 9, I'm doing the same thing. So at those moments in time, I'm measuring the same two variables. So all variables are measured simultaneously. And that helps us understand how constructs are related to each other at a given age or moment in development. Okay, so think of verbal skills over the first 5 years of life, right? So I can we tell 5-year-olds maybe to use their words, and you probably wouldn't tell a baby, an infant that is like 11 months old, you probably wouldn't tell them to use their words. So if we looked at those two things as a snapshot at certain moments in time, we could see a relationship, correlation, and then as the child's growing, we expect to see some change maybe in those two variables. But the important key with this is that they're cross-sectionally measured simultaneously. An autocorrelation is an association between the same variable measured at different points in time. So maybe I have a large set of children, a group of children, and I'm looking at a rating called peer difficulties. So maybe you have a parent giving this information and they're rating their child on the difficulties they have in getting along with their peers. So I have only one variable this time. It's not like the other one where I was looking at a relationship between two. But what I'm looking at is the stability or the consistency of that variable over time. And it is going to answer questions like, is this trait or behavior stable across years? Or does an earlier score help predict a later one? Those might be questions we would ask with this type of design. And then the last one that we're going to discuss in here is cross-lag correlations. And that's when we have associations between different variables where one is measured at an earlier point and the other is measured later. So maybe we look at their pro-social behavior at age 7 and we want to use that to predict how they're going to act with their peers at age 8. And this is really important for testing a directional hypothesis. And it also goes into causal relationships. So we might look at something like this, kindness at an earlier age. If a child shows more kindness at an earlier age, is that more likely to reduce later social challenges 5 years down the road? So in research, the gold standard for establishing causality is an experiment. So to have an experiment, a true experiment, you've got a couple of things that have to be met. You've got to have random assignment and you've got to have an independent variable that is manipulated. And by manipulated, I mean purposeful change or purposeful holding constant or setting a level of that independent variable, like medication, um, Adderall at 10 milligrams, at 20 milligrams, at 30 milligrams. The problem, however, is that we can't always do experiments. There's two reasons why. There's many other reasons, but there's two big ones. First, it's not always ethical, especially when it comes to random assignment. So think about some of the negative behaviors that we know of out in the world, like smoking cigarettes. So I can't randomly assign pregnant women to groups and tell this group over here, you're smokers, you're going to smoke. I don't care if you've never smoked before, now you're a smoker. And this group over here, you're not a smoker. It's not ethical. And then it's also not always realistic because some variables we can't manipulate them. So what becomes a substitute in those situations might be longitudinal studies where we observe real world behaviors over time. We don't have manipulation or random assignment or both. But there's issues with that too. First of all, we don't have any control over confounding variables because I can't select for and screen out for those confounding variables, right? And then any association that I find could simply be correlational and not causal. All right, so let's get into how we do these calculations for regression in Jamovi. And you're going to need to probably pay close attention to this, and you might want to go back and refer to these notes because there are several statistics that you have to run at once to be able to get the full picture of that regression. So let's dive right in. So say you're a researcher and you want to know if the number of hours college students sleep per night predicts their GPA. Okay, we've got lots of data out there on the importance of sleep, but this particular researcher is interested in knowing, do the hours of sleep predict their GPA? Not is there a correlation, but can it predict it? So what they do is they collect data from 50 students, and at minimum they record data on how many hours they slept per night and what their GPA was at the end of the semester. And what we want to do is answer this research question. Does the amount of sleep predict GPA in college students? And I didn't go into the null and the alternative hypothesis here because hopefully by this point they're clear. The null hypothesis would say that there is no prediction. You can't predict. No amount of sleep predicts GPA. And the other one would be it does. So how do you do this in Jamovi? Well, you're going to go to analyses and you're going to go to regression and you're going to pull linear regression down. And what you're going to do is you're going to move over in this particular data set, there's only two variables, semester GPA, and to the dependent variable, semester GPA, and then to sleep hours to that covariate. So you have linear regression, there's your dependent variable, semester GPA, and covariates, sleep hours per night. We're going to go in under several different places here and make sure we've got certain things marked. So under model fit, which is right here, I couldn't fit all of this on the slide, but you're going to make sure that R, R squared, adjusted R, and then the F test are selected. And then you're going to need to go under model coefficients, and you're going to need to mark ANOVA test and standardized estimate. And we're going to get an output that looks like this. The first thing you're going to focus on is your model fit measures. And there's only one predictor in this particular scenario. So that one predictor is sleep hours per night. So I have an R and an R squared and an adjusted R square, and then I have an F value. And that F value has been compared to critical values established with our degrees of freedom and our significance level, which is 0.05 for everything in this class. And you can look at this p-value out here to the side. P is less than 0.001. So what does that tell me? It tells me first that this model is significant. And second, in that line right there, I can find out that the variance in college students' GPA explained by sleep is about 52%. And I got that from right here at that R squared. So now we know the model was significant, but we need to look at sleep being a significant predictor of GPA by doing or examining this model coefficients output down here. Okay, so you have an intercept and you have sleep hours per night. And what we're looking at, this is a t-test, okay? And it's going to have its p-value right there. And we have not gone over t-tests in this class because this is non-experimental, and y'all just got to bear with me and go if I ask you to look at this down here. This is where I'm asking you to pull it from the model coefficients. But is sleep a significant predictor? Yes, it is. T equals 7.19, and the p-value is less than 0.001. So if I go back here and I look at this estimate, 0.231. For every hour of sleep per night, the GPA increases by about 23 points. That is where that came from, right there. So that example was all well and good, right? I had one predictive variable, sleep hours. But like I've said multiple times during this presentation, nothing happens in a vacuum, and it's very unlikely that that's the only variable affecting the GPA. And actually, it only attributed for like 50 something percent of the variance. So what's making up the rest of the variance? Well, that's where researchers come in and start adding things to the model from the data that they've collected in order to come up with a model that best explains what they're looking for. Now, we're not going to get that far complicated in it, but we are going to add one more variable there so that you can see how we look at the change in our statistics. So this time we're going to look at the same thing, but we're going to try to predict college student GPA using two linear regression models. The first model, we're going to look at the thing we just looked at, hours of sleep and their GPA. In the second model, we're going to add another predictor, and that's going to be class attendance percentage. So now we're trying to see, okay, if I attributed for 53% of my, or 50 whatever percent of the variance in that first model, if I add another variable to it, can I predict more? Are these models significant? So we're going to compare those two models. So your two models are this, model 1, only sleep hours, and model 2, sleep hours plus class attendance. And when we run our test in Jamovi, we're looking to see if either of the models is significant. So we're going to look at the model fit measures. So it says, according to the results, look, both models are significant. I have model 1 and I have model 2. But look at the difference. Model 1 about 52% of the variance was explained by sleep hours. I added class attendance in percentage, and my R square only went up 0.5, or now it's 0.530. So if I round the first one, it only went up by 1 percentage point. Now, why does this still stay, the F statistics here, why does it still say that it is significant? Well, if this model with one variable was significant to begin with, and I added another variable to it, obviously it's still going to be significant. What do you predict would happen if I took away hours of sleep? Well, I'd be left with only that percentage attendance, and it's not going to be significant. You could look at this and tell, because the difference between the R squared is not, it's negligible. So this is where you get to examine that difference when you're running this regression this way. We've added class attendance. It says we evaluate if adding it significantly improved the prediction. So we look at model comparisons, and you know you're looking at model comparisons because it says model comparisons, but you also have this delta R squared, which by adding that variable, we only can now explain an additional 1.15% of variance. And you can look over here and see your F is 1.15 and your p-value is much greater than 0.05, so it is not significant. So adding class attendance percentage to this model didn't help it. You can also go into your model coefficients to even just to see if that predictor in that second model was significant. So you can see down here that sleep hours remains, because of this t-test, it remains significant at the 0.05 level. But class attendance, it did not. It is not significant. It is not a significant predictor. So let's go over your assignment really quickly. It is not very long for the regression portion. Like I said earlier, we may go back in and touch upon this a little bit next week. But for now, again, this assignment's due next Friday. So let's look at just an overview. So when you go into Canvas, you're going to see the assignment. You're going to have a downloadable Word document that's titled Regression Assignment. You're going to download it. And you're going to also download the data file. And you're going to use Jamovi to conduct the analyses. It's the same analysis that we just did here, the one about linear with one predictor. I'm not going to ask you to look at two predictors and add them right now and see if it changes. We'll get to that maybe next week. When you're done, I want you to answer the questions in the document, type your answers, save it, and then upload it, and you're done. So remember, if you have any questions, please feel free to reach out, and I hope you enjoyed this presentation. Bye.